Hello everyone, this is Miss Berlin and this lecture video is all about deriving kinematic equations. Unlike our previous lesson that we just derived the equations by translating the narrative description into mathematical or algebraic expressions like for example the concept of speed or velocity, the motions or the equations that we will be encountering must be derived, okay? Must be derived so that it will help you to make or understand where the equations came from. That is why we are deriving equations. Why that particular equation is suitable for a particular problem. You have to know that. Now, let's say, for example, that we have a runway here, and this runway has an airplane, and it says to have to be moving at a constant acceleration. When we say that this airplane is moving at a constant acceleration, we mean to say that it is now moving, for example, at 1 second at 2 meters per second. At 2 seconds, it is moving at 4 meters per second. And at 3 seconds, it is moving at 6 meters per second. Right? So this is constant because as you can see, the quantity is increasing as the time went on by scale of 2, right? And then the next thing that we need to do is we have to express this narrative description into graphical expression using, of course, the velocity time graph. So we have here the velocity, we have the time, right? And then let's say that the initial velocity is at here, okay? And a constant acceleration has a direct or straight diagonal line. Okay? And this is an acceleration because we have here the acceleration equals velocity, change in velocity over time, right? And velocity, for example, we have 6 meters per second over time, the 3 seconds. What's that? What's the acceleration? That is 2 meters per second squared. That is acceleration. So we have here the constant A for this graph. And then we have to plot the final velocity here. Okay, final velocity. And then this is the initial velocity here. This is the time. This one here. That's the time. Now let us derive the first equation. The first equation is getting the velocity. And in order for us to do that, we have to know or we have to manipulate the equation for acceleration, which is A equals the delta V or the rate of change in velocity over time. Now, in this case, we will be having here, expand that is A equals V sub F or final velocity minus initial velocity over time. And then in order for me to get the final velocity, we should use or we should multiply time at both sides of the equation equals v sub f minus v sub I over t multiplied to t as well. And then cancel this one, cancel the time here. And then you will be left out with at equals v sub f minus v sub I. Now what I need is the final velocity, alright, or the velocity. So what we need for this equation, for this to be eliminated, we have to add initial velocity on both sides of the equation because whatever you added on the other side of the equation must be added as well on the other side of the equation, v sub I equals v sub f minus v sub I. You added v sub I here, then you need to add v sub I here as well. Now, negative, positive cancel. Alright? On that note, you will have acceleration and time plus initial velocity equals final velocity. This is the first equation. Now, at times, the A is expressed as G, small g, which is related to free fall value. The acceleration due to gravity related to g is 9.8 meters per second squared. Then, it is positive when the object is dropped from above, going down, but then it is negative when the object is thrown upward because it resisted the gravity. It opposed the gravity. Now, let us derive the second equation. The second equation that we need to derive is the displacement. Okay, we can't use the VT here or velocity multiplied to time because here the airplane, for example, is moving upward, and in problems involving 3D motions and 2D motions, this is not applicable. Okay, so we will be using or we will be deriving based on the graph here that we have, and the displacement is said to be equivalent to the area under that graph. area. Displacement is equivalent to the area under that graph. And this is the graph. Under that, this is the area here. And we have here the initial velocity. Let us plot the initial velocity here as well by drawing a dashed line here. And therefore, this is the initial velocity. This one. V sub I as well. They have the same length, right? And by doing that, we will be having two shapes here, right? We have what? We have rectangle, we have the triangle, correct? And in order for us to find the displacement, we will be getting the area of these two shapes. So let us use X instead of D, but you can use D. That's okay. So area of rectangle plus area of, what's the other shape? Triangle. All right. Now, the next thing that we need to do on this case is get the formula for the area of rectangle. What is the formula? Length times width, right? And then plus the area of the triangle. What's the formula for this? Area of triangle. 1/2. 1/2 multiplied to base times height, correct? Now, we need to alter the variables given here based on the variables of the graph here, alright? So, for the rectangle, what's the length of the rectangle? We have here, this one is time below, time. So we have here the initial velocity for length, v sub I. And then for the width, here, this is the time, correct? Now, let us 1/2. What's the base of the triangle? This one. Yes, this is time. Okay, multiplied to the height. For us to find the height of the triangle, we have to note first that this is the final velocity and it has the equal length on the other side. This is the final velocity as well. They have the same length, both sides, right? And for us to find the triangle, we need to look on the first equation. The first equation says that the final velocity, this one, okay, is equivalent to initial velocity, this one here, this part here, plus something here, right? So again, final velocity is equivalent to the sum of the initial velocity here plus the something here. What's the something on this equation? That is 80, right? So therefore, the height of the triangle, not the whole shape of this one, but the triangle alone is acceleration and time. And then simplify, you have v sub I t plus 1/2 t multiplied to 80, that is 80 squared, right? 80 squared because t times t is t squared, right? Alright. And then x equals, simplify, v sub I t plus 1/2 times 80 squared. 1 times 80 squared is 80 squared. Let me, 80 squared over 2 times this one, 2 times the denominator, imaginary denominator, that's 2. 80 squared over 2. This is the second equation. Okay? Now, as you can see, this equation, sometimes this one, 80, can be used as GT for free fall problems. You just have to alter that whether of 9.8 meters per second squared or negative 9.8. Now, if you will observe or if you will look at the equation, you can see that these equations here are very much dependent of time. There are time variables present, right? You have VIT, GT, you have AT. Alright, there are time, but then there are problems, kinematic problems, that does not involve time. And therefore, you have to derive an equation that is independent of time. And that is what we are going to do now. Let me erase this. For us to get that equation independent is independent of time, we need to get the total area here. When we say total area, we don't need to dissect this part into two shapes, but rather the whole graph or whole area under that particular graph. Alright? So that will be S equals the area of the shape under the graph, which is this one. This is the shape, right? And this one is the area of trapezoid. What's the formula for the area of trapezoid? That is 1/2 times base times the height or the sum of the heights, h1 plus h2. Correct? This is the formula. And of course, we have to substitute the variables here based on the variables on this graph. Correct? So to do that, you will have 1/2. What's the base of this trapezoid? Time, right? And as you can see for the heights, As you can see, we have two parallels here, initial velocity and then the final velocity as a whole. We have two parallels. So that will be v sub f plus v sub I. Yes, you can alter that because it has an associative property for the sums, right? But then this is the equation. And the next thing that you need to do, we still have the presence of time. We need an equation that is independent of time, devoid of time for the sample problems or problems that time is not involved. All right, so we have to eliminate this. And for us to eliminate that, we have to substitute a particular value for that. And for that particular value, we need to manipulate this equation of acceleration. Acceleration equals v sub f minus v sub I over time. And then let us multiply time on both sides. A multiplied to time equals v sub f minus v sub I over time multiplied to time. Cancel here. You will have 80 equals v sub f minus v sub I, right? And then what we need is just the value for time. So we need to divide both sides with a so that we can eliminate the acceleration and obtain the time equation for time. So cancel, you are left now with t equals v sub f minus v sub I. This is your value that must be substituted on this t here so that we can eliminate the t value on this equation. Now, substituting that, let us substitute. You will have here t, rewrite s equals 1 half, and then the value is of the t here is this one, that is over a. V sub f minus v sub I over a. Okay. And then multiply v sub f plus v sub I, right? And then simplify s equals 1 half, and then multiply vf, multiply to vf, that's vf squared, right? And then vi multiplied to initial velocity, that's vi squared. Of course, negative because they have different signs, vi squared over a. We can still simplify this 1 half. All right, we have here, let me arrange the 1 half. 1 half, 1 half multiplied to vf squared minus vi squared over a. 1 multiplied to the numerator, you just have to copy that, vf squared minus vi squared over 2 times the a, that is 2a. This is the third equation or the third formula. Sometimes this is 2g instead of 2a for free fall problems. Alright, it is for deriving kinematic equations. Thank you.